Yo, welcome back. So today I'm at the job where I drove the earth rod in. I also done the fuse pull video, and I'm back here today to do some earth electrode testing. So before, if you've seen those other videos, if not, I'll put links to them. But if you saw them, I just got an earth fault loop impedance value, and that was fine. It ticked the box basically. It allowed us to sign the job off, get a cert done, and it was all sweet. But knowing what I'm like, I knew straight away this is on home soil. It's an easy job to get to. I wanted to come back and basically do some earth electrode testing the proper way. Now, I actually done a video on this before with Paul Meenan where we run through the full process, all three methods, and use some fancy kit at a railway station with conduit discs. So if you want to check that video out, that will be below as well. But this time it's going to be me on my own, verifying my own installation, and yeah, without Paul looking over my shoulder, making sure I'm not messing up. I've got my test kit, I've got Guidance Notes 3, and I've got a stake kit, basically a Q-Tech stake testing kit. So we've got all the gear, no idea. We'll get out the van, we'll start getting started, and we'll see how far we get with this earth electrode testing. I was actually at a party yesterday, a family party that required some entertainment for little ones, so I've actually got loads of random stuff in the back of my van. I've got it out of the way for now, but that's cool. That's got to go back in. Let's get the test kit, get that shut, and then we're back to where I was. So they haven't filled it in or anything. There's my earth rod down there. Probably going to clear some of the rubbish out of the way there. Taking the roof off this place at the minute, so debris everywhere. That's why I come today. It's a Sunday, lovely day, midday. But yeah, I'm going to clear this out. I've got this open, so we're going to isolate the installation, and then yeah, run our leads up there. I think I drove 2 rods in, so you want to do 10 times your rod distance, so about 20 meters for my current probe, I believe. And we'll double check that, but yeah, and then that will take me probably up to where they're building the shell of those houses up there. So then I'll need to go in between in these stones, and yeah, super dry day, so should be worst possible conditions. Interesting. That will do. So this is my test kit. I've got the Q-Tech KT6060L. It's got earth electrode testing, and basically I've got my current or my red lead goes in there, my earth lead goes in the middle, and then my voltage lead or my S lead, sorry, P lead goes in here. So yeah, that's how I'm going to do the test. I've also got this lovely little Vito, which has got my stake kit in. So it does come in a Q-Tech bag, but I'm just a bit of a diva, to be honest. So I've just got it in this Vito. But yeah, I've got my 2 probes, I've got my current lead, my voltage lead, and then my earth lead as well. So we'll run them out together. And like I say, there's 2 meters of rod in the ground, so 10 times 2, I believe it says, or it says, sorry. The distance between test spikes is important. If they are too close together, their resistance will overlap. In general, results may be expected if the distance between the electrode under test and the current spike, C2, is at least 10 times the maximum dimension of the earth electrode system. For example, 30 meters for a 3 meter long rod electrode. So what they're saying there is, yeah, if you've got 3 meter rod, you want 30 meters, 1 meter rod, 10 meters. I've got 2 meters of rod, so I want 20 meters, and that's between C2, which is our current probe, our current spikes. That's going to be the furthest. And what we're doing basically is we've got 3 leads. One lead's going to connect onto the earth electrode. That's our earth lead, our point of earth, our electrode under test. Then we're going to run a lead 10 times the distance of the earth electrode system. So that's going to be our current lead, and that's going to go 20 meters that way. And then we're going to have our voltage lead in the middle, and that's going to test that resistance basically, and then the earth electrode tester is going to calculate that. Throughout the test we actually move the voltage lead 10% this way, 10% that way, but yeah, you're just going to move that middle lead about, then that yellow lead about, just to see what results you get and obviously verify the system. You also want to make sure you know your leads. I think what I'm going to do is, just because it's easier, I'm going to measure the resistance of the leads and be sure to minus that. I think that's going to be the easiest way. But yeah, make sure you know your leads, because obviously you're dealing with like long old leads, up to 50 meters worth of leads, so you want to make sure you factor that out of your resistance readings. We'll get the system isolated and then we'll start getting the tester set up. Right, so this is an easy isolation for me. I'm going to shed the load of the board, I'm going to bang that off and turn that back on. Yeah, RCDs aren't tripping. Obviously we're going to test for dead, but that's just a great indicator straight away. We don't want to, I mean, I'm doing this for the purposes of the video, but there's literally no parallel paths. There's no parallel paths and there's no danger to the installation if I did disconnect the earth, to be honest with you, because it's just these 2 socket circuits. So yeah, it wouldn't affect anyone. However, we are going to do it properly, just to, yeah, to explain the process properly. So, there we go. That can come off. Go grab my testers, quickly prove for dead, and then we're just going to disconnect this earth basically from the system, which would negate any parallel paths. The reason why we isolate is that if you run into a house or a building or something, you just disconnect the earth, especially on a TT system, that would cause massive issues. Yeah, unless you've got an alternative source of earth that you can utilise, you're going to have to isolate the installation. And then once the installation's isolated, you then want to disconnect your earth from the MET, because you don't want to pick up any parallel paths. Now we're literally putting stakes into the ground. So, you know, you've got to imagine if there's a copper gas pipe or some structural steel that goes into the ground or something like that, you're literally going to have parallel paths there, literally acting like earth electrodes, so it's really going to mess with all the results. So it's a big deal to, yeah, obviously isolate, and secondly to disconnect from the MET so that you can get a pure reading on your electrode. Now we could just disconnect at the electrode end, that's cool, but on most installations it might not be that simple, so I'm just going to show me disconnecting here once I prove dead. Prove. Lovely. And then we'll go between earth and live, earth and neutral, and then go between these 2 as well. Prove one more time. Bosh. And there we go. We're proven dead and we are ready to disconnect the earth. So nothing dramatic, literally just going to undo that, pop that out and just make sure it's sitting freely away from everything, and then that is the earth disconnected. We can now get our tester set up and start getting our stakes in the ground ready to test. Right, so we wanted one of these and we're going to go for the red lead, but for now I'm just going to pace this out. So that is our rod there. I'm just going to do 21 meter steps. 2, 3, 4, 5, 17, 18, 19, 20, about there. Okay, I'm going to hammer that in a little sec, and then we'll just pace back 10 meters from here. 1, 2, 9, 10. Put a bit of wood there, so that's where I'm going to want my other one. Obviously I'm going to hammer them in, but that's just what I just wanted to show you the process of actually walking these through. Now this is hard under here. Must have been a driveway or something, so that's going to be interesting. Maybe we can find a soft bit, but yeah, I'll go get the hammer and we'll see where we can get that in. So you'll notice as well, like this end of the shaft on the T is like sort of tapered, it's smaller, and that's where we're going to clamp onto. I'll show you the clamps obviously in a minute, but yeah, I thought that was cool on the spikes, how they're designed. They're not just, you know, random spikes, they've actually been machined to yeah, try and provide the best reading that they can. Let's go get the next one hammered in. This one's going to be interesting. Not having it. Right, well, I know from the last video, this whole area got CAT scanned basically. That's how we knew we could just drive the rod in. So I think I'm just going to drill a little hole. Get that in. It's going to be interesting though, because I don't know how solid this is and how far it goes. But yeah, it's not going in as it is. So that's our 2 probes in. Now I just need to start running these leads out. So the red one's going the furthest one, that's our current lead, and then the yellow one's our voltage lead, that's going to the middle. I'm going to send the drone up and you can watch me pace these out. Right, so leads are in, current leads all the way over there, voltage leads in the middle, again clamped onto those tapered bits of the auxiliary spikes, and then we're just going to follow these back to our mains position, which is also where our rod is, and you'll see that I have it connected onto the rod there too, the rod that we're testing. Over here I have my KT66 connected up, ready to go, and again we've got our current lead in here, our voltage lead there, and then our earth lead in there. So I'm going to fire this up. You probably won't be able to see the screen at all just because of the day we're on with the glare, but we'll see. So I've got it on earth mode, and then you've basically got 2 wire and 3 wire. So the 3 wire is the test that we're doing. I believe 2 wire is what they call the simplified test, which is where you can't use the auxiliary spikes and you basically test between the earth electrode and like a water bond or something. I may be wrong, that's what I sort of gathered from the manual, but yeah, we're on 3 wire and we're ready to go. So I'm just going to press test, and we've got 16.64 ohms, which is a great reading, especially on a dry, dusty day like today. That is an absolutely fantastic reading. It's not too far off what we got originally anyway. I remember it was around 16 ohms. You don't want anything over 200, and ideally, to be honest, around 20 ohms is what keeps the NIC happy and stuff like that. So on a dry, dusty day like today, using the full extent, you know, we're a good 20 meters away, that is a smashing reading, but that is only our first reading. So I'm going to jot this one down, and then we're going to move the probes, the voltage probe or the voltage test spike 10% that way, and then we'll move it 10% this way. So basically 2 meters further that way, 2 meters back towards us. We'll get 2 more readings, and then we'll be able to do an average from there. Right, this one was fun to do. 1, 2. So we want to be about there. Let's pull this off. Yank this out. I mean, I did have to hammer the hell out of it to get it in there. There we go. I mean, we're in the sand here, but there'll probably be stuff underneath. Yeah, I'll get the hammer drill out then. I'm not going to go too mad here because, to be honest, I'll probably get a great reading regardless. Let's get this clamped on. There we go. We're ready to go again. So our first reading was 16.66. Now I'm going to go again. We've got 16.84 ohms. So let's do plus 10%, 16.85, but we won't split hairs over that. And now we want to do minus 10%. So we'll now go and move the current probe 2 meters this way, or 10% this way from the middle position, not from where it was, and we'll test again. Right, 16.2 ohms. 16.20. So there we go. I mean, to be honest with you, I can tell you the average now is going to be around 16.5, 16.4. But I'm happy with the reading there of 16.6. If they were changing drastically between them, then yeah, you'd want to get down to the nuts and bolts about it, you know. Say for instance, you had to drive in 5 meters of rods, so you had a 50 meter sort of test distance, and yeah, they were jumping like, you know, 30, 40 ohms between them or whatever, then yeah, the averages would really matter. But 16 ohms is an amazing reading anyway, and of course, you know, we're talking half an ohm each way, if that. By doing, you know, the 10% plus or minus. So yeah, that is pretty much it. I'll just double check the book. When me and Paul Meenan done it, what we done is we actually drew a map of, like, yeah, the distance between the earth electrode and the test points, and we actually done, like, I don't know, 10 or 12 tests and took an average. But the difference there was they had a conjure disc system, so those conjure discs, they don't go that deep. They're flat discs that lay in the ground, earthing discs. And basically, yeah, we done a larger sample area, I guess, purely because there was 9 discs across a 25 meter run, and yeah, we took values throughout the whole distance. Now, what was funny there was the first conjure disc, and the closest one to the intake room, was actually one of the highest results, and that was because the conductor to the first conjure disc was insulated. Therefore, it would have to double back on itself to the first conjure disc to pick up there, so it would actually be a longer path, a longer reading, if that makes sense. And then all the ones in between, all the links in between to the other conjure disc were bare, so that obviously helped out. But yeah, it's interesting earthing, really interesting, and I'm glad I could come here today and do this for you. So I'm just checking 3 readings are taken. Firstly, with the potential spike T2 inserted midway between the electrode under test and the current spikes. That's the first one we done. And then secondly, with T2 moved to a position of 10% of the overall electrode current spike distance back towards the electrode under test. So we've done that second, or we've done that third, sorry. And then last, T2 moved in a position 10% of the overall distance current spike from its initial position between the electrode under test and T1. So yeah, we've done it backwards, but it doesn't matter what order you do it in, I suppose. Yeah, then it says, by comparing the 3 readings, a percentage deviation can be determined. This is calculated by taking the average of the 3 readings, finding the maximum deviation of the readings from this average in ohms, and expressing this as a percentage of the average. Okay, so it's not just about getting an average then. The accuracy of the measurement using this technique, typically 1.2 times the percentage deviation of the readings. If it is difficult to achieve, the readings shouldn't differ more than 5%, which they don't, to be fair. Okay, well, let's get an average then. So averages are fairly simple. What you want to do is you want to take 16.66, add 16.84, add 16.2. That gives us 49.7, and then we want to divide that by 3 because we took 3 measurements, and that gives us 16.56. So like I guessed, you know, it's around 16.5. And then this is where it's going to lose me, and I'm going to make a massive fool of myself on camera. I'm going to expose how little I know. Calculated by, find the maximum deviation of the readings from this average in ohms, and expressing this as a percentage of the average. Right, okay, so the maximum deviation from 16.56 is probably 16.2. Let's write down our average of 16.56, and then what we need to do is we need to take our value, our one with the biggest deviations, that's 16.2, divide that by 16.56, and then we need to times that by 100, 97.8. So, and then if we reverse that, that's going to be 2.2%. 2.2%, I believe. Let's just spin you around. So what we have here is our first value of 16.66, our plus 10 value of 16.84, and our minus 10% value of 16.2. Those three added together divided by 3 gives us an average of 16.56. I then take the one with the most deviation, which is 16.2. I divide that by our total value, and that gave me a value of 97.8. And obviously that's going to be a deviation of 2.2% to make that 97.8 100%. So we now have a 2.2% deviation value. Let's see what it says. The accuracy of the measurement using this technique is typically 1 times the percentage deviation of the readings. It is difficult to achieve an accuracy measurement better than 2%, and is inadvisable to accept readings that differ by more than 5% in this event. To improve the accuracy, cool. So yeah, we've done it. You know, we haven't deviated more than 5%. It's difficult to get better than 2%. So we've got 2.2% to be fair, and it says if it gets harder, the test must be repeated with a larger separation between the electrode under test and the current spike. So, you know, we're bang on the money there, and it's a great value as well. Like, if it was 150, 200 ohms, then I'd be stressing out, but 16 ohms is an amazing earth volt loop impedance value anyway. So yeah, I think we've done it. You know, that is earth electrode testing. I think I'm going to do a follow-up tutorial video like I normally do, you know, where I just sit there and waffle on and use footage from today. But it was good to just do it together, do the process together, get the Q-Tech out, and yeah, just show you it in real world practice. Obviously you can get the Q-Tech KT66DL, all of the tools in this video, and the Earth Spike test accessory kit, all from Loadout. We sell all of that stuff, so if you want to get the kit to do this test yourself, then yeah, the link for that will be below. Hopefully you've learned something today. I certainly have, and I'll catch you guys on the next one.